So now let's try to find the scattering angle phi prime. Okay. So first of all, from the figure, okay, so you can see the relations between this phi prime and the theta max. Okay. So because this is phi prime and this is also phi prime. Okay. So, and you can clearly see that theta max plus phi prime is equals to pi, right? So 180 degrees. So in other words, this phi prime is equals to pi minus 2 times theta max. Okay. So that is, if we are able to find out the theta max, that would be enough for us to get to phi prime. So theta max, as I mentioned previously, is related to the asymptotic line of this hyperbola. Okay. So now, remember how did we get to the equation of hyperbola in chapter 3, part 1? Okay, so this was the relation that we used. Okay, so we perform this integral to find out the relation between theta and r. And for the case where energy is greater than 0, that would be a hyperbola. Right, so that means that in this integral, right, so the r theta refers to the coordinates of any point on this hyperbola, on the hyperbola. So now I'm going to use this relation again, but this time I want to use it as a definite integral, right? So that means I have the lower limit and the upper limit set. That means that for the lower limit, I need to pick a point, pick a theta value, right? And then correspondingly, I have to pick the r value. And similarly, for the upper limit, I need to pick another theta value, and correspondingly, I need to pick the r value. So the lower limit, I pick this r mean and theta naught, right? So the r mean theta naught is actually the coordinate of P. Okay, so this P. So the coordinate is r mean theta naught. So remember, the reason why I call this r mean is because this is the point of minimum distance, right? So between P and O. So this distance is r mean. So, and the upper limit, I pick this r2 and theta 2. That is the coordinate of a point over here. So now imagine that you are picking a point which is very, very, very far away, right? So it's almost infinitely far away from this point P. Right. So then in that case, this R2 will tend to infinity. But however, the theta 2 won't go to infinity. It will go to an asymptotic value. Okay. So in fact, what you can see is that if this, so first of all, let me look at theta naught. Okay. So theta naught, what is theta naught? Theta naught actually is this angle over here. So this angle is theta naught. And now what is theta 2? Right, so theta 2 So this purple one would be theta 2. You could imagine that if you take R2 really far away, right? So then the theta 2 maybe looking something like this, right? So if R2 is really infinitely far away, this theta 2 actually tends to pi. And now this theta 2 minus theta naught, which is this angle, this green angle over here, right? So will tends to theta max, right? So because if this theta 2 tends to pi, so that means that this purple line is essentially a horizontal line, right? So then this angle over here is just the same as theta max. Okay, so then taking this limit, the left-hand side, right? So the left-hand side, this one, right? So tends to theta max. So as long as you take this out to go to infinity. So remember the scattering angle phi prime is pi minus 2 theta max, right? So then it's pi minus 2 times this integral over here. So this integral can be calculated, right? So it really depends on the u of r, right? So if it is 1 over r squared, again, then of course can be calculated. And now R mean. So the R mean is also a number that we need to figure out, right? So but R mean can be expressed in terms of this initial velocity V0 and the impact parameter B. Okay, so by considering the conservation of energy and angular momentum. Right, so the initial energy, right? So the initial energy is 1/2 mv0 squared, right? So the potential energy is 0 because it was infinitely far away. And now, as it gets to the closest point to the force center, which is point P, then the total energy of the particle is given by this, right? So because at the closest point, this term of the kinetic energy is 0 because R dot is 0. So then from this relation, well, it might be complicated, but in principle, you could find R mean. So now, if I just consider the special case of this 1 over r squared, it can be shown that phi prime given by 2 minus arc cosine of this, right? So this integral is arc cosine of this one. So this one, I'll just leave it as an exercise for you, right? So you actually don't need to do the whole integral one more time, right? So you just need to consider the property of your hyperbola, right? So from this one. So, and consider the limit when r tends to infinity. So the next thing I need to talk about is a concept which is known as the differential cross-section of scattering. So considering the following experiment, okay, so just like initially I talked about the Rutherford scattering experiment, is that I have a beam of particles, right? So a beam of particles, that means that I have many of them, right? So like a shower of particles, okay? So uniformly distributed across and covering a wide range of impact parameters. And now, in particular, right, so if I consider one of the particle, right, so this one, so, and it comes in and it repelled by this force center, right, so, and then it goes, this band like this, right, and then reach this region over here. So then you could imagine that if I consider another particle in the beam, right? So for example, this one over here, then it might bend down and reach a region somewhere here, right? So, and then again, if I consider another particle just basically next to this one, maybe it will go like this. Right, so bend a bit up compared to that one. It really depends on the nature of this force, but let's say it bent over here. So there are many particles, and then essentially, right, so each particles so will go to slightly different directions. Okay, so essentially the question I'm trying to ask here is that how many of them will go over here, right? So how many of them will go over here? How many of them go over here, and so on, right? So it's like a distribution. I want to know the distribution of the scattering angle phi prime. Okay. So now I will just erase something and again consider the one particle that I have in this figure, okay, which is this one. So this particles, which has a particular velocity and the impact parameter, right? So it gets to this region d sigma, right? So it passes through this d sigma before the scattering happened, right? So this red plane over here is a virtual plane that I call S. Okay, so and this d sigma is a particular is a small element of this plane over here. And as this plane, as this particle passes through this small region d sigma, as it goes like a trajectory like this and reach this region here. Okay, so and this one, just imagine that this is a particle detector that I set up over here, and I will call this area dA. Okay. So now I have this is one detector, but you have to imagine that I have many detectors. Okay, so what you need to consider is that I have another detector here, I have another detector here, another detector here. So how are they distributed? So just imagine that you actually have a sphere, have a spherical surface centered at this scattering center O. right? So I have this sphere, and just imagine that you are putting many detectors to cover every portion of this spherical surface. Okay, so many small detector TA cover the entire sphere. Okay, so that is all the detectors, they will be able to capture all the particles, so no matter what value of the phi prime that you have. Okay. So, and for each a detector over here, this dA. So just imagine that this d sigma, right? So the location is really far away from O, right? So and this dA is also really far away from O. Okay. And now this, what is this d sigma? Okay, so this I'm sorry, not d sigma, this d omega. So this d omega is known as the solid angle of this dA. So what is solid angle? So solid angle is defined as this dA divided by R squared. So what is this capital R? So capital R is the radius of this spherical surface. Okay. So this is R. Right, so this d omega defined as this dA divided by R squared. Okay. So this d omega is not an area. So the dA is area. This d omega, the solid angle, differential solid angle. So so there's the slide here, which I introduced the concept of solid angle. Right. So we know what an angle is, first of all. Right. So when I talk about an angle, so you could imagine that I'm asking like there are two lines, right? So and how wide I am opening these two lines apart, right? So you could just imagine that you construct a circle, right? So and then I put one line here and then another line over here, and I ask what is the angle between these two lines, and that this angle, right? So can be defined as this arc length over here divided by the radius of the circle. So that's the angle. So what about solid angle? Well, solid angle is now you instead of considering a circle, now you consider a spherical surface like this. And then now so the angle, right? So is this quantity, so between these two lines, right? So now what I'm having over here is not two lines, but I have a cone. Okay, so opening a cone over here, that cone, right? So the edge, the tip of the cone, right? So is at this point O, right? And it's open up like this, and that cone, right? So when it touch the circumference, the surface area of this sphere, so it will cut out an area A, right? So the solid angle of this cone is defined by this area that you cut out divided by this radius R squared. So in this picture, I'm drawing a circular cone, right? So the base is a circle, but it does not have to be. So it can be the base can be a rectangle, a triangle, and other shape, but you can always define the solid angle by this area divided by R squared. Okay. So then the differential cross-section is defined as the ratio between this d sigma divided by this d omega. Okay. So then this is the quantity that we are going to study next time.